topic is about ground rods and an article that makes claims about listed versus non-listed ground rods and potential code implications. The article makes several claims that need to be addressed. Claim number 1 states that non-listed ground rods are not required to meet any performance standards and may not provide adequate protection. While it is true that non-listed ground rods do not undergo the same rigorous testing as listed rods, they do meet the minimum requirements of the National Electrical Code, or NEC, and are considered safe for grounding purposes. Claim number 2 states that copper-clad steel rods are prone to corrosion and should not be used in aggressive soil conditions. Copper-clad steel rods are approved for use in the NEC and have been successfully used in various soil conditions. Proper installation and maintenance, including corrosion protection measures, can mitigate any potential concerns. Claim number 3 states that Underwriters Laboratories, ORAL, and Canadian Standards Association, or CSA, listed ground rods are the only rods that guarantee a minimum conductivity level. While it is true that listed rods undergo conductivity testing, non-listed rods can also meet the NEC minimum conductivity requirements when properly manufactured and installed. It is important for inspectors to rely on the actual requirements of the code and not solely on opinions expressed in industry articles. The NEC currently permits the use of both listed and non-listed ground rods, provided they meet the specified standards. Grounding electrodes are a critical component of electrical safety, providing a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers and fuses. The National Electrical Code, specifically Article 250, dictates the requirements for grounding and bonding, ensuring a safe and effective electrical system. Ground rods, often made of copper-clad steel, are a common type of grounding electrode. Their primary function is to establish a connection to the earth, dissipating fault current and stabilizing the electrical potential of the system. The NEC outlines specific requirements for ground rod installation, including the minimum length and diameter of the rod, as well as the depth to which it must be driven into the ground. The code also addresses the number of ground rods required and the spacing between them. While the NEC provides these minimum requirements, the choice between listed and non-listed ground rods is a matter of ongoing discussion and interpretation. Listed ground rods have been evaluated by independent testing laboratories such as UL or CSA and have been found to meet specific performance and safety standards. These standards typically include requirements for conductivity, corrosion resistance, and mechanical strength. Non-listed ground rods, on the other hand, have not undergone the same rigorous testing and evaluation process. While they may still meet the minimum requirements of the NEC, their performance and durability may not be as well documented or guaranteed. The issue of corrosion resistance is particularly important, as ground rods are often installed in direct contact with soil, which can be corrosive. Copper-clad steel rods are commonly used due to their combination of conductivity and strength. However, the copper cladding can be damaged or compromised, exposing the underlying steel to corrosion. In aggressive soil conditions, such as those with high levels of salinity or acidity, corrosion can occur more rapidly, potentially reducing the effectiveness of the grounding electrode. The NEC addresses the issue of corrosion in Section 250.10, which requires that grounding electrodes be protected from corrosion. This can be achieved through various means, such as using corrosion-resistant materials, applying protective coatings, or installing the ground rod in a location with less corrosive soil. The conductivity of the ground rod is another important factor to consider. The NEC requires that grounding electrodes have a sufficiently low impedance to ensure that fault current can flow freely to the earth. This impedance is affected by the material, size, and length of the ground rod, as well as the conductivity of the surrounding soil. Listed ground rods typically undergo conductivity testing to ensure that they meet minimum performance requirements. Non-listed ground rods may not be subject to the same testing, so it is important to verify that they meet the NEC conductivity requirements. When selecting ground rods, it is important to consider the specific conditions of the installation, including the soil type, climate, and potential for corrosion. In some cases, listed ground rods may be a better choice due to their enhanced performance and durability. In other cases, non-listed ground rods may be adequate, provided that they meet the minimum requirements of the NEC and are properly installed and maintained. It is also important to consult with a qualified electrical inspector or engineer to ensure that the grounding system is designed and installed in accordance with all applicable codes and standards. In addition to ground rods, other types of grounding electrodes are also available, such as ground plates, ground rings, and concrete encased electrodes, also known as euphograms. Each type of electrode has its own advantages and disadvantages, and the best choice for a particular application will depend on the specific conditions of the installation. Ground plates are typically made of copper or galvanized steel and are buried horizontally in the ground. They offer a large surface area for contact with the soil, which can improve their conductivity. Ground rings are typically made of bare copper wire and are buried in a loop around the perimeter of a building or structure. They provide a continuous grounding path and can be particularly effective in areas with poor soil conductivity. Concrete encased electrodes are installed within the concrete foundation of a building or structure. They provide a very stable and reliable grounding connection as the concrete helps to protect the electrode from corrosion and physical damage. The NEC allows for the use of any of these types of grounding electrodes, provided that they meet the specified requirements. The code also allows for the use of multiple grounding electrodes connected together to form a grounding system. This can improve the overall effectiveness of the grounding system and provide redundancy in case one of the electrodes fails. The installation of grounding electrodes should be performed by a qualified electrician or other trained professional. Proper installation is essential to ensure that the grounding system is effective and safe. The NEC provides detailed requirements for the installation of grounding electrodes, including the depth to which they must be buried, the spacing between them, and the methods for connecting them to the electrical system. It is important to follow these requirements carefully to avoid any potential problems. In addition to the installation requirements, the NEC also addresses the maintenance and testing of grounding systems. Grounding systems should be inspected regularly to ensure that they are in good condition and that all connections are tight and corrosion-free. The NEC also requires that grounding systems be tested periodically to verify that they are providing adequate protection. This testing can be performed using a ground resistance meter, which measures the resistance of the grounding system to earth. A low resistance reading indicates that the grounding system is effective, while a high resistance reading indicates that there may be a problem. If a problem is detected, it should be corrected immediately to ensure the safety of the electrical system. Grounding and bonding are essential components of a safe and effective electrical system. By following the requirements of the NEC and consulting with qualified professionals, it is possible to design and install a grounding system that will provide reliable protection against electrical shock and other hazards. The ongoing discussion about listed versus non-listed ground rods highlights the importance of staying informed about the latest developments in electrical safety and technology. By understanding the requirements of the NEC and the performance characteristics of different types of grounding electrodes, it is possible to make informed decisions that will improve the safety and reliability of electrical systems. The importance of grounding in electrical systems cannot be overstated. It is a fundamental safety measure that protects people and equipment from electrical shock and damage. A properly designed and installed grounding system provides a low impedance path for fault current to return to the source, allowing overcurrent protective devices to quickly clear the fault and prevent further damage. Grounding also helps to stabilize the voltage of the electrical system, reducing the risk of voltage surges and other disturbances. The NEC provides comprehensive requirements for grounding and bonding, covering all aspects of electrical system design, installation, and maintenance. These requirements are based on years of experience and research, and are constantly updated to reflect the latest advances in technology and safety practices. Adherence to the NEC grounding requirements is essential for ensuring the safety and reliability of electrical systems. Failure to properly ground an electrical system can have serious consequences, including electrical shock, fire, and equipment damage. In addition to the NEC, other standards and guidelines also address grounding and bonding, such as those published by the Institute of Electrical and Electronics Engineers, or IAEI, and the National Fire Protection Association, or NFPA. These standards provide more detailed information on specific aspects of grounding and bonding, such as grounding electrode system design, surge protection, and electromagnetic compatibility. It is important for electrical engineers and technicians to be familiar with these standards and guidelines to ensure that they are using the best practices for grounding and bonding. The selection of grounding electrodes is an important part of grounding system design. The NEC specifies the types of grounding electrodes that are permitted, as well as the minimum size and installation requirements. The most common types of grounding electrodes include ground rods, ground plates, ground rings, and concrete encased electrodes. Ground rods are typically made of copper-clad steel or stainless steel and are driven into the ground. They are a simple and cost-effective grounding solution for many applications. Ground plates are typically made of copper or galvanized steel and are buried horizontally in the ground. They offer a larger surface area for contact with the soil than ground rods, which can improve their conductivity. Ground rings are typically made of bare copper wire and are buried in a loop around the perimeter of a building or structure. They provide a continuous grounding path and can be particularly effective in areas with poor soil conductivity. Concrete encased electrodes are installed within the concrete foundation of a building or structure. They provide a very stable and reliable grounding connection, as the concrete helps to protect the electrode from corrosion and physical damage. The choice of grounding electrode will depend on several factors, including the soil conditions, the size of the electrical system, and the required level of protection. In some cases, it may be necessary to use multiple grounding electrodes connected together to form a grounding system. The installation of grounding electrodes should be performed by a qualified electrician or other trained professional. Proper installation is essential to ensure that the grounding system is effective and safe. The NEC provides detailed requirements for the installation of grounding electrodes, including the depth to which they must be buried, the spacing between them, and the methods for connecting them to the electrical system. It is important to follow these requirements carefully to avoid any potential problems. In addition to the installation requirements, the NEC also addresses the maintenance and testing of grounding systems. Grounding systems should be inspected regularly to ensure that they are in good condition and that all connections are tight and corrosion-free. The NEC also requires that grounding systems be tested periodically to verify that they are providing adequate protection. This testing can be performed using a ground resistance meter, which measures the resistance of the grounding system to earth. A low resistance reading indicates that the grounding system is effective, while a high resistance reading indicates that there may be a problem. If a problem is detected, it should be corrected immediately to ensure the safety of the electrical system. Grounding and bonding are essential components of a safe and effective electrical system. By following the requirements of the NEC and consulting with qualified professionals, it is possible to design and install a grounding system that will provide reliable protection against electrical shock and other hazards. The ongoing discussion about listed versus non-listed ground rods highlights the importance of staying informed about the latest developments in electrical safety and technology. By understanding the requirements of the NEC and the performance characteristics of different types of grounding electrodes, it is possible to make informed decisions that will improve the safety and reliability of electrical systems. Let us now talk about the specifics of ground rod installation and the NEC requirements, focusing on key sections of Article 250. Section 250.52 addresses the types of grounding electrodes that are permitted. As mentioned, these include ground rods, pipe electrodes, plate electrodes, and other types of electrodes that meet specific requirements. The NEC specifies that ground rods must be at least 8 feet in length and have a minimum diameter of 5/8 inch for steel or iron and 1/2 inch for non-ferrous materials. These dimensions ensure that the ground rod has sufficient surface area to make good contact with the earth. Section 250.53 provides requirements for the installation of ground rods and other electrodes. It states that ground rods must be driven into the ground so that at least 8 feet of their length is in contact with the soil. This ensures that the ground rod has sufficient contact with the earth to provide a low impedance path for fault current. The NEC also requires that ground rods be installed at least 8 feet apart from each other. This spacing helps to minimize the interaction between the grounding fields of the rods and ensures that each rod is effective in dissipating fault current. In situations where it is not possible to drive the ground rod vertically, the NEC allows it to be buried at an angle not more than 45 degrees from vertical or buried horizontally in a trench at least 30 inches deep. This provides flexibility in situations where obstructions or other factors prevent vertical installation. The connection of the grounding electrode conductor to the ground rod is also critical. The NEC requires that the connection be made using listed connectors or by exothermic welding. Listed connectors are specifically designed for grounding applications and provide a reliable and corrosion-resistant connection. Exothermic welding creates a permanent metallurgical bond between the conductor and the ground rod, providing an even more robust connection. Section 250.64 addresses the requirements for the grounding electrode conductor, which connects the grounding electrode to the electrical system. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in Table 250.66 of the NEC. The grounding electrode conductor must be securely connected to the grounding electrode and to the neutral bus or ground bus in the service equipment. Section 250.68 provides requirements for the connection of the grounding electrode conductor to the grounding electrode. It specifies that the connection must be accessible and made in a manner that ensures a permanent and effective ground path. The connection must also be protected from physical damage. Section 250.70 addresses the methods for bonding metal enclosures and other non-current carrying metal parts of the electrical system. Bonding is the process of connecting these metal parts together to create a low impedance path for fault current. This helps to ensure that fault current will flow quickly and reliably back to the source, allowing overcurrent protective devices to operate and clear the fault. The NEC provides detailed requirements for bonding, including the size of the bonding conductors and the methods for making the connections. Proper bonding is essential for preventing electrical shock hazards and ensuring the safety of the electrical system. Section 250.104 addresses the bonding of metal water piping systems. Metal water piping systems can provide a path for fault current and must be bonded to the electrical system to prevent electrical shock hazards. The NEC requires that the metal water piping system be bonded to the grounding electrode conductor or to the neutral bus in the service equipment. The bonding connection must be made within 5 feet of the point where the water pipe enters the building. Section 250.118 lists the types of equipment grounding conductors that are permitted. Equipment grounding conductors are used to connect the metal enclosures of electrical equipment to the grounding system. This helps to ensure that any fault current will flow quickly and reliably back to the source, allowing overcurrent protective devices to operate and clear the fault. The NEC specifies that equipment grounding conductors must be made of copper, aluminum, or other approved materials. They must also be sized according to Table 250.122 of the NEC. Section 250.122 provides the requirements for the size of equipment grounding conductors. The size of the equipment grounding conductor is determined by the size of the overcurrent protective device protecting the circuit. The NEC provides a table that lists the minimum size of the equipment grounding conductor for various sizes of overcurrent protective devices. It is important to select the correct size of equipment grounding conductor to ensure that it can safely carry the fault current. Section 250.130 addresses the methods for grounding receptacles and other electrical outlets. Receptacles and other electrical outlets must be grounded to provide a safe path for fault current. The NEC specifies that receptacles must be grounded using a grounding conductor that is connected to the grounding system. The grounding conductor must be connected to the grounding terminal of the receptacle and to the grounding bus in the panel board. Section 250.146 provides requirements for the use of ground fault circuit interrupters, or GFCIs. GFCIs are devices that are designed to protect people from electrical shock. They work by monitoring the current flowing in a circuit and detecting any imbalance between the hot conductor and the neutral conductor. If an imbalance is detected, the GFCI will quickly trip the circuit, cutting off the power and preventing an electrical shock. The NEC requires that GFCIs be installed in certain locations where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor areas. Section 250.166 provides requirements for the grounding of separately derived systems. Separately derived systems are electrical systems that are powered by a source that is separate from the main electrical service, such as a generator or a transformer. The NEC requires that separately derived systems be grounded in the same manner as the main electrical service. This helps to ensure that the separately derived system is properly grounded and that any fault current will flow quickly and reliably back to the source. In summary, Article 250 of the NEC provides comprehensive requirements for grounding and bonding electrical systems. These requirements are essential for ensuring the safety and reliability of electrical systems and for protecting people from electrical shock and other hazards. It is important for electrical engineers, technicians, and inspectors to be familiar with these requirements and to follow them carefully. The ongoing discussion about listed versus non-listed ground rods highlights the importance of staying informed about the latest developments in electrical safety and technology. By understanding the requirements of the NEC and the performance characteristics of different types of grounding electrodes, it is possible to make informed decisions that will improve the safety and reliability of electrical systems. Let's shift focus to practical considerations for selecting and installing ground rods, addressing common challenges and offering solutions. Firstly, soil resistivity is a critical factor. High soil resistivity increases the resistance to ground, making it harder to achieve an effective ground. Soil resistivity varies depending on soil type, moisture content, and temperature. Sandy or rocky soils typically have higher resistivity than clay soils. Dry soils have higher resistivity than moist soils. Cold soils have higher resistivity than warm soils. To reduce soil resistivity, several techniques can be used. One is to add water to the soil. This can be done by watering the area around the ground rod or by installing a water pipe near the ground rod. Another technique is to add bentonite clay to the soil. Bentonite clay is a type of clay that has a high water holding capacity, which can help to reduce soil resistivity. A third technique is to use a chemical ground rod. Chemical ground rods contain chemicals that dissolve into the soil, reducing its resistivity. Secondly, the number of ground rods is a consideration. If a single ground rod does not achieve the required resistance to ground, multiple ground rods may be necessary. The NEC requires that a second ground rod be installed if a single ground rod does not have a resistance to ground of 25 ohms or less. The ground rods should be spaced at least 6 feet apart to avoid interaction between their grounding fields. Thirdly, corrosion protection is paramount. Ground rods are susceptible to corrosion, especially in aggressive soil conditions. Corrosion can reduce the effectiveness of the ground rod and eventually lead to its failure. To protect ground rods from corrosion, several measures can be taken. One is to use copper-clad steel ground rods. Copper-clad steel ground rods have a steel core that is covered with a layer of copper. The copper layer provides corrosion protection and the steel core provides strength. Another measure is to use stainless steel ground rods. Stainless steel ground rods are highly resistant to corrosion. A third measure is to apply a corrosion-resistant coating to the ground rod. There are many different types of corrosion-resistant coatings available. Fourthly, proper connection is crucial. The connection between the ground rod and the grounding electrode conductor must be secure and corrosion-resistant. The NEC requires that the connection be made using listed connectors or by exothermic welding. Listed connectors are specifically designed for grounding applications and provide a reliable and corrosion-resistant connection. Exothermic welding creates a permanent metallurgical bond between the conductor and the ground rod, providing an even more robust connection. Fifthly, accessibility for testing is important. The ground rod should be installed in a location that is accessible for testing. This will allow you to periodically check the resistance to ground and ensure that the ground rod is still effective. The ground rod should be installed in a location where it is not likely to be damaged or disturbed. Common challenges in ground rod installation include rocky soil, buried utilities, and limited space. Rocky soil can make it difficult to drive the ground rod into the ground. If you encounter rocky soil, you may need to use a ground rod driver or other specialized equipment to drive the ground rod. Buried utilities can pose a safety hazard during ground rod installation. Before driving a ground rod, it is important to locate any buried utilities in the area. You can do this by calling your local utility companies or by using a ground-penetrating radar. Limited space can make it difficult to install the ground rod in the required location. If you have limited space, you may need to use a shorter ground rod or install the ground rod at an angle. By addressing these practical considerations and challenges, you can ensure that your ground rod installation is safe, effective, and compliant with the NEC. Remember to always consult with a qualified electrician or other trained professional if you have any questions or concerns. Finally, let's touch upon the future trends in grounding technology. Firstly, smart grounding systems are emerging. These systems use sensors and communication technology to monitor the performance of the grounding system in real time. This allows for early detection of problems and proactive maintenance. Secondly, advanced materials are being developed. Researchers are working on new materials for ground rods that are more corrosion resistant and have higher conductivity. These materials will improve the performance and longevity of grounding systems. Thirdly, improved installation techniques are being explored. New techniques are being developed to make ground rod installation easier and more efficient. These techniques will reduce the cost of grounding and make it more accessible. Fourthly, standardization efforts are ongoing. Efforts are underway to standardize the requirements for grounding systems worldwide. This will improve the safety and reliability of electrical systems globally. These future trends promise to further enhance the safety and effectiveness of grounding systems, ensuring the continued protection of people and equipment from electrical hazards. In conclusion, understanding the nuances of ground rods, NEC requirements, practical considerations, and future trends is crucial for anyone involved in electrical system design, installation, or maintenance. By staying informed and adhering to best practices, we can ensure the safety and reliability of electrical systems for years to come.